Dr. Wiebke Baille study a diploma of study of civil engineering at Bauhaus University, Weimar in Germany in 2002. And from 2002 to 2005, she works as a project engineer in a geotechnical engineering company. And since 2005, she worked as a research assistant at Chair of Soil Mechanics at Bauhaus University, Weimar. And since 2009 at Ruhr-Universität of Bochum. And in 2014, she studied a PhD degree for Doctor of Engineer at Ruhr University in hydromechanical behavior of clays, and the major is the significance of mineralogy.
Okay, thank you. Then please, it's your turn. Take your lecture.
Okay, just one question. Do you see the slides in the right manner, or do you see the...
Yes.
Yes, okay. So first of all, thank you for the invitation, especially to Dr. Maybe you allow me some few words about the work which I will present. It's on the effect of fines content on the undrained shear behavior of sandy soils. And this work was mainly performed by my colleague or former colleague Mega Rahemi, who did her PhD on this topic, and it was initially supervised by Professor Tom Schanz. So when I was invited for that workshop, also in the memory of Professor Guyen Panda, I found in my records that I had the opportunity to meet him at a workshop in Utrecht, University of Utrecht, and yeah, where Professor Schanz was invited, and we had some contribution there as well, and he sent me there to participate, and so I had the opportunity to meet Professor Pande as well. Okay, so that's obviously the connection life is doing. But now back to soil mechanics. So as the motivation for the work which I will present, which is mainly, let's say, geotechnical engineering work, in Germany we had some severe events of liquefaction, which are related to former open pit mines of brown coal, essentially. And as you might know, as the when the active mining is finished, the sites are remediated to be used again for the public. And this process is still going on in the eastern part of Germany, for example, and will start also now or soon in the western part, in the Rhinish brown coal revier, since Germany has decided to leave completely the brown coal in 2038. And all these remediation works are going on or will start depending on this progress of mining. As it was already shown in former publications, there is a significant effect of fines content on the liquefaction behavior, and we have this in the case of dynamic or cyclic loading on the soil and also monotonic loading. I think we know a lot of cases where liquefaction is triggered due to earthquakes, so cyclic and dynamic loading, but this is not the case here in these two examples, since this region is not prone to seismic or to seismicity. So the source is what we call as static liquefaction, or maybe some trigger due to earthworks or artificially induced cyclic or dynamic loading. So this is a slide just to illustrate the framework in which we are moving here in this study. So the concept of critical state and the different types of behavior depending on the initial density of the soil. So usually we have two very distinct mechanisms, which are the dilative behavior, which we can observe in the pore water pressure, which is firstly slightly increasing, but then decreasing. And in the contrary, we have the contractant behavior, where the pore water pressure is continuously increasing until the soil will liquefy. There's also a kind of intermediate mechanism which occurs at, let's say, intermediate state of these samples, where the soil is first being contracted and then dilative, and this mechanism is also called limited liquefaction. So on the right side, we see the stress paths corresponding to these three mechanisms, and the orange path, so the continuous decrease in effective stress, is representing the liquefaction mechanism. The so-called instability line is defined by the inclination of a line which goes through the peak point of the measured or observed deviator stress during liquefaction path. And at the end of the deformation, when we have large deformation and no further stress change or pore water pressure change, this state is the well-known critical state. So based on this concept, in the void ratio effective stress space, there is the definition of the state parameter psi null as the difference of the initial void ratio of the sample to the critical state line. And essentially, when the initial state of a soil sample is above the critical state line, this soil element or soil sample is susceptible to liquefaction, whereas it is not when the density is higher as the density at critical state. And so in terms of void ratio, we are below of the critical state line. So in the framework of the critical state line concept, and together with the definition of the instability line, we can, or usually, or some people distinguish between the so-called cyclic mobility and the liquefaction mechanism itself. So here difference is made between the initial state in terms of initial deviatoric stress. If we remain in a region of deviatoric stress due to loading, which is smaller than the undrained residual shear strength, we call this mechanism cyclic mobility, whereas when the loading and independent, whether it is cyclic loading or monotonic loading, is in a range larger than the undrained shear strength in residual state, we speak of liquefaction or flow liquefaction. So what is shown here is an example of triaxial test results, both cyclic and monotonic, of typical sand from this open pit mine area in Lausitz area. In English, it is called Lusatian area. And what we can see here is when we have a cyclic loading of a sample in an initially loose state, we see here the deviatoric stress or pore water pressure. So the blue line is the pore water pressure, the red line is the measured deviatoric strain, and the black line is the applied cyclic load. So this special sample failed after 23 cycles of load, and in the deviatoric stress versus P dash plane, we see here the behavior, and we could observe that the failure or the liquefaction of that sample occurred at the point where this instability line was reached, and it completely failed down. So we see that the deviatoric stress was essentially above the range of the and that's why the sample liquefied when the so-called instability line was reached. And here you see a monotonic triaxial test result of a sample with the same initial conditions, but the difference is the monotonic loading. And from the monotonic test, we determine the inclination of this instability line through the peak point of that stress path. So from the monotonic test, undrained triaxial test, we can determine characteristics which are also relevant for cyclic loading of a material. And this is also valid for samples with fine content. And in the following, what was done is that a concept of equivalent state parameter was applied, which takes into account fines content after Tevanayagam and Raman and Low. And this enables the determination of an equivalent critical state line and instability line, taking into account fines content. So what was the material about in the work of Negar Rahemi? So she performed about 50 triaxial tests, which were mainly isotropically consolidated and undrained. And here in this diagram, you can see the void ratio E over fines content FC for the different mixtures which she has tested. The grain size distribution is shown here on the right side. She prepared different mixtures of Postun sand and silt, where you can see the microscopic pictures, as well. And the fines content chosen were 0%, so pure sand, 10% fines content, 20, 30, 40, 50, and 100. And these are the according grain size distribution of these mixtures. So when we summarize results, and we can check whether the samples behave according to the well-known critical state concept. So we have plotted the mean effective stress on the vertical axis versus this state parameter psi 0. And here you see the different results. Black symbols show the fine content of the pure, the result of the pure scent. Red symbols are for the 10% and so on. And what we can observe is that in case of all fine contents, all samples have shown the liquefaction stress path or liquefaction behavior when the state parameter was greater than 0. So the results qualitatively fitted well to the concept. What was further observed is that for the fine content 100% and the initial state parameter greater than 0, the liquefaction occurred despite the dense initial state. And for the region of fines content between 0 and 0.5, in few examples, we have observed the so-called limited liquefaction when the initial state was around the critical state line, so psi was approximately 0. Now we have tried to, or we have applied the plotted the results in terms of so the different, separately for the different fine content ranges versus effective stress, and also in the stress plane QP dash. And what we see is that what was also already observed by others is that in the range where the coarse grains are dominant, the samples showed the critical state lines in a range from top to down to bottom with increasing fines content. And for the fines content range larger than the threshold value, so in the range where the fines are dominant, we see different linear behavior of the critical state line. In the effective stress deviato stress plane, we can see no effect of the fine content on the friction angle at critical state. So in this slide, it is shown what is meant by the region dominated of the coarse fraction or by the fines fraction. For the quantitative application to calculate an equivalent void ratio, these two cases inside the red frame are considered. And so in this case, we see that the contribution of the fine grains to the load transfer is partly there. So some of the fines, they can contribute to the load transfer and some they cannot. Whereas here, the assumption is that the coarse grains are inside a matrix of the fines and partly they will contribute to a kind of reinforcing they will somehow reinforce the whole soil matrix simply by their presence, even when there is not always contact between them. So according to these two assumptions, the critical state lines are normalized for these two ranges of fines content. So in the first case, where the coarse grains are dominant, we apply this equation to calculate the so-called equivalent void ratio E star. And this number B is a factor or a value which quantifies to which extent the fines contribute to the load transfer inside the whole soil matrix. And this factor, yeah, can be determined differently. There's one suggestion by Rahman et al. To calculate this B value as a function of fines content, this threshold fines content, and also factor R, which is a ratio of D50 of the fines and D10 of the coarse fraction, and two other parameters K and mu, or the second variant which was applied in this study to look for the best fit of B for that case when we have the least deviation of all points here from a normalized critical state line. So you can see here the parameters B determined by these two methods, and the other parameters describing the shape of the critical state line in the E star P dash plane, which were determined for the different fines content here. And then we have the other range for fines content higher than the threshold value. And here another approach was applied where the factor M signifies the measure for the reinforcing effect of the coarse grains inside the fines matrix. And the data allowed to apply this equation, and we could find parameters which were resulting in a normalized critical state line. So the sense of this normalization is that using this equation, you can calculate then critical states for all for samples for any fines content. So without the need to determine it experimentally before. So otherwise you would need always to determine all the critical state parameters for any fine content to be able to predict something. But once you have normalized the critical state line in terms of E star and found equivalent void ratio, which takes into account the fine content, then there is, in theory, less need to determine experimental parameters. So further use of this concept is also that it was suggested to predict the instability ratio, so the stress ratio eta ES at this peak point of instability in the undrained liquefaction path as a function of the initial state parameter psi null. And here we can see that again there is a quite good relationship for this mixture tested here in the lower fines content range, but for the higher fines contents we cannot find a relationship where we can state, okay, there's a nice fit of all the data in terms of the functional dependency of the stress ratio eta as a function of state parameter psi. So by this, I am already at the end of the presentation, and I will summarize that it was clearly shown that the Fiennes content affects the critical state line in the void ratio stress diagram, but no effect on the critical state friction angle was seen in the P-Q plane. There is the normalization of the critical state line is possible separately for the coarse grain and the fine grain dominated region. And yeah, for further work, one can ask oneself what are the physical parameters which affect these somehow empirical values of B and M. So how they can be justified by some physical meaning. So in the prior presentation, we have seen nice slides about effect of shade, for instance, or surface roughness. So for sure, all these mechanisms play a role probably for this behavior here. And to use these concepts for applications in real problems on site, like we have seen in the open pit mines, we need to have an exact knowledge about the state of the soil in situ. So we need good methods to be able to measure in situ void ratio, density, Fiennes content, stress state, and so on. So there is a potential application of that relationship of the stress ratio eta IS with respect to the state parameter psi, which could be useful in the frame of monitoring for quantitative evaluation of measured pore water pressures and estimation of liquefaction potential. So that's my presentation, and when you have questions, you are welcome to ask questions.
Thank you for thank you for your lecture. And if anybody has a question, please.
Yes, thank you so much for this very deep lecture. And I would like to ask one question, and I would have one comment. And for the comment, I would like to show something on the screen. So I would like to ask you to leave the share position. And
No
I am telling the question that probably yes, I managed to share. So my question is that this instability line was defined by yourselves in your study, or this is a well-known concept?
No, this is a concept which is already established.
Okay, thank you. So it was very interesting and very nice. So I am so happy to have this presentation. And I just would like to mention this picture that long time ago, I was once in Bochum, and you gave me some data from the result of Negar Rahmi. And I represented this data in the grading entropy theory, in the grading entropy diagram. I am not sure that everybody is familiar with this diagram. So I'm just telling some short sentences that in the upper line, you can see the grading entropy diagram and the internal stability on grain structure stability criterion of Lorentz. So according to Lorentz, a mixture can be stable if the relative base entropy parameter A, which is in the horizontal axis, is larger than 2/3. And if it is smaller than 2/3, it can be unstable. And there is a transitional zone, like nearly a triangle. This is a transition zone which is valid for larger uniformity coefficient if there is a wide grading curve. So in the left-hand side, I put the 20 30–40% of the fine. And you can see as this mixture had in the test of Nagar-Rahimi, and if the fine content is increasing, the internal structure is starting to be increasingly unstable. And finally, the 50 seems to be unstable. And in the right-hand side, I tried to compute a kind of probability from the static test. So the probability to be liquefied, and you can see that it is also increasing. So if we had a mixture with 10% fine, this probability was 40. But if we had 40–50%, the probability was larger than 18. So probably sometimes in the future, we can go into the details of this representation and into your very deep analysis, and we may come out some conclusion. So it is exactly the same what you mentioned, that when we have too many small grains, in this case, the internal structure is starting to be different. So there is a change from coarse to fine to coarse. And probably this line is the division line, not quite sure, but we can try out. So thank you. This was my comment, and I didn't really want to make a long comment. And I would like to give back the word to the chair and to Wiebke.
Okay, yes, so it would be good, or of course we are open to use the data for your concept in terms of entropy, and I would be very curious to see how this works in detail. Mm.
Thank you. And just one more comment, that we recently made a report for TC 201 about river dikes, flood levees, and we also found the liquefaction phenomenon extremely important. So this could be in another collaboration, at least just for this very small problem. So I will send some email about this if you don't mind. So we can use this your very nice research results in this research also. So thank you very much.